Hello? Hello, hello, hello. Okay, audio's on. Good. Morning? Printf? Yeah, okay, all right. Now we're making progress. So, how's the lab? You know how Printf works yet? So, I hope if you're stuck and way confused, maybe both of those at the same time, I can't help way confused on the Printf lab because that code is just confusing. So if you're not stuck and way confused, perhaps you're okay. But if you're stuck and way confused, come and talk to me. I'll be in the office this afternoon, right after my next class, which ends at 2:30. So does anybody have any questions they want to ask? Okay, Garrett? Guys? Yep.
Find out their false, we have to put that in our write-up or we just skip over those.
Okay, say it again.
We have a lot of if statements we have to evaluate, they call functions to return values and stuff like that. If those return false, do we need to put that in the write-up or?
Okay, so the question is, you have a whole bunch of if statements that don't impact the flow of control because they don't evaluate the true, then you don't have to trace the function calls that you don't call. But it would be good for you to justify why the if statement evaluates to false. So specifically in the check and it macro, there are two if statements. You should explain why both of them evaluate the way that they do. Okay, the first if statement checks the FP arrow underscore data field to see if it's null. It's not null. Why isn't it null? The second if statement says, is the FP arrow underscore data underscore arrow s dit underscore s dit init field, is that equal to 0 or not? It is equal to 0 initially. Why is it 0? If you don't chase the initialization path on this guy, you aren't going to be able to explain those two things. Okay? Other questions? No one's taking it? All right, so today we're going to talk about stuff for the next lab, Lab 3. We've got a good 30 pages of notes to blast through, and it's all really good stuff. And here, this is where we really start talking about low-level coding. We haven't really been talking about low-level coding to date. This is really low-level coding. So we're going to talk about the ARM architecture. We're going to talk about interrupts. We're going to talk about how the ARM architecture, our chip, and our board interact to support interrupts. And then we're going to talk about the application of interrupts and how we're going to use them in Lab 3. Okay, so we have a board. Our board is called the TS7200 board. It has the following features. It's got 32 megabytes of RAM on it. It's got an 8 megabyte flash chip on it. It's got a DIO header. DIO stands for digital input output. Sometimes you see this as GPIO, general purpose IO. It's got an LCD header, but that's a set of pins that come out on the board that you can plug in a ribbon cable and connect that to an LCD screen if you wanted to. There's an A to D on there. We don't use the LCD. We don't use the A to D. It also has Ethernet, USB peripheral support. Those guys can be used under the Linux kernel that's on there on the board that comes from the manufacturer, but we don't make use of those. It also has that big black strip on there. That big black thing is a PC104 header. So that's another bus that's on there. So anybody know the history of PC104? It's you remember you got the PCI bus on your motherboard inside your PC. Before the PCI bus, what was there? ISA. That's PC104, the ISA bus, but just in a smaller form factor. Okay, so the CPU that we use is an EP9302 chip from Cirrus Logic. Wait a minute, I thought this was an ARM. It is an ARM. ARM doesn't build hardware. Okay? ARM is what you call a fabless semiconductor company. What they do is they design hardware. They don't build it. Okay? They design cores. Those cores they then sell to hardware designers. The core isn't a specification of a complete processor. It's a specification of most of the processor, the internal pipeline, and it's got some inputs and some outputs. But usually people stack on peripheral devices, especially in an embedded context, around the core. And so Cirrus Logic is a company that leased an ARM core from ARM and then made a bunch of peripheral devices around it and fabbed a chip. The chip is called the EP9302. Okay? So the little chip you see on the TS7200 board is not an ARM chip, it's a Cirrus Logic chip. Okay. What is the ARM core that we're using? It's an ARM 920T. The 9 means ARM 9. That's the 9 series of ARM cores. T means it supports thumb. Thumb is the name for ARM's 16-bit instruction set. Just close the door, Mitch. It'll open by itself if you don't. So, what that means, the T means that the ARM chip that we have, the Cirrus Logic chip, it can support both a 32-bit instruction set, which we are using, and it can support a 16-bit instruction set. We aren't using that. So here's a general diagram of the chip. You've seen this a whole bunch. You've got the PC104 header down here at the bottom. You've got the other headers here at the top. You've got the RS-232 port right there, USB, the RJ45 for Ethernet, the EP9302, the reset button over there. You've got this big box for putting in a compact flash card. You've got a flash chip here and a RAM chip there. So this is the 32 megabytes of RAM, and then you've got your 8 megabytes of Strata flash there. Okay. So the EP9302 from Cirrus Logic is just about the same thing as an EP9301. The only difference between the two chips is that the EP9302 has more space for a bigger boot ROM. We don't deal with a boot ROM. Technologic Systems, who manufactured the board, has inserted the boot ROM code into the boot ROM, and we don't get access to it. We can't fiddle with that. And I think that's just unfortunate. So that's just the good stuff. You use your boot ROM to configure your RAM. So your processor has to know what RAM chip it's talking to, so it knows the timing, and it can do, for example, if it's DRAM, it configures its DRAM controller to refresh the RAM at the right rate. If you don't get that set right, well, your chip is just hosed. It's not going to work right. So there are some things that are initially configured in the boot ROM of your chip. When you're developing a board in an embedded context, you have to get your boot ROM right, otherwise you're just toast. Okay? But we don't mess around with the boot ROM. The boot ROM is responsible for bringing the chip up, and it will initially configure and run Red Boot. Okay? So once Red Boot's in place, then that's the bootloader that is allowed to facilitate download with the host or to load Linux, as is the case in here. So it knows how to interact with a flash to extract stuff and run stuff. Okay. Because the EP9302 is mostly the same thing as the EP9301, we use the EP9301 documentation. Why? Because there is no EP9302 documentation. It's just they just have the big document for the EP9301 and say, well, yeah, the 02 is just the same thing. Okay. So there's a block diagram here. So there are what I'm showing you right here, there are 3 PDF files that are available on Blackboard that document our board, our chip, and our core. All right, so we have the EP9301 user's guide that I'm showing you right here. Has this block diagram on page 23. What this shows you, this is the chip documentation, okay? So this is the whole chip. Right here, this box in the middle labeled ARM 920T, that's the core. So that's the ARM core. It's got the memory management unit, it's got an instruction cache, a data cache, and the processor pipeline. It's got this AHB-APB bridge, and then it's got all these peripheral devices that are embedded in silicon on the chip. So, for example, the vectored interrupt controllers, which we'll be beating to death today, your SDRAM controller, JTAG, USB host, okay, timers, analog to digital converter, UARTs, all this stuff. All these devices are there to help this chip be usable in embedded environments. They do different jobs. We're not going to be using most of those peripheral devices. Sometimes we use them implicitly. Sometimes we could use them for different types of applications, but for the most part in this class, we're not going to be explicitly calling out the features of various peripheral devices. We'll use the timers. We'll use the vectored interrupt controllers. Okay? See if anything else there we're going to make use of. Probably not. Okay. All right. Okay. Again, we need to distinguish between board, chip, and core. We have documents for the board. That is the TS7200 guide. We have documentation for the chip, which is the EP9301 user's guide, and then the documentation for the core, which is the ARM reference manual. The ARM reference manual is where if you want to look up an assembly language mnemonic, you can get it in the ARM reference core, or in the ARM reference guide that documents the core. Okay, you don't need to read those documents. They're there for your reference. You can look stuff up in them if you want to. You don't have to dig through them unless you really want to. Okay, the ARM processor. It's a 5-stage pipeline, on-chip instruction and data caches. It supports interrupts and multiple types of interrupts. So, what's an interrupt? I'll tell you a good example of the interrupt. The interrupt is where you're talking on the phone to, well, who knows who you're talking on the phone to, and your 3-year-old daughter comes up to you and says, "I need to use the potty." That would be an example of a non-maskable interrupt. You have to stop. You have to take her to the potty. There's no other option. Otherwise, you're going to have a big old mess on your hand. An interrupt is a whole lot like your child that comes up, "Hey, hey, 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 I need some attention, hey, 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 hey," and it keeps on yelling at you until you pay attention. Okay? That is what an interrupt is. It's an asynchronous function call. It's how the external world comes up and says, "Hey, I need attention." Okay? So what is an interrupt? It's an asynchronous function call. It's code that gets triggered by the outside of the normal flow of the program. There are different sources of interrupts. Usually it's not your daughter hooking up to your processor saying, "I need to flip the potty" interrupt. Normally what it is, it's maybe like a timer, where you've configured the timer to say, "I need to know whenever X amount of time has expired. I'm going to go do my thing. Mr. Timer, you do your thing, and you just tell me when this much time has happened." But an interrupt is something that is designed into the system so that you can be notified or you can be made aware of when some event happens. And this event isn't something that you cause or you trigger. It happens outside of the normal flow of the program. So your program is minding its own P's and Q's, doing its thing, executing instructions, doing the math, whatever it's doing, and then some event happens. And all of a sudden that causes your program to stop what it's doing and go and do something else, to take the kid to the potty, to go and manage the timer, to, oh yeah, maybe I better command the brakes to start braking again, or whatever it is your application's doing. You go and you do that, and as soon as you're done, then you resume doing what you were doing before. Okay, so how do you configure interrupts to happen? Well, when you're dealing with interrupts, what you're going to do is you're going to register your intent to process an interrupt with some hardware, okay? So before you start doing your thing, you tell that hardware, when something happens, I want to do this. When this happens, I want to do that. When that happens, I want to do this. Now, I'm going to go mind my own business and do my thing, but as soon as any one of those events happen, I want to trigger this function or that function or this other function. Okay. Running this function, that function, the other function involves you have to freeze the execution of your current program that you're running. Your process has to stop doing what it's doing. You have to go and run the XYZ associated with the event that you've registered, and then you unfreeze and resume the execution of your program when you're done. Okay? The idea of handling an interrupt is that you have to do it quickly. The reason why is because the intent is that an interrupt is some event that happens and you handle it very quickly and go back to doing what you were doing. If it requires a long amount of processing, what you do is you just set up some flags that say, by the way, you've got some extra work to do, and as soon as you resume what you were doing, you recognize the fact I've got to handle more work associated with the event that happened. But interrupts are supposed to be quick and be resolved quickly. Why do you need to freeze and unfreeze the processor? What does this freezing business mean? You only have one processor. You can only do one thing at a time. So you can either run your program or you can handle an interrupt. You can't do both at the same time. So the problem is that sometimes when you're handling an interrupt, you need to access the state of the processor. The state of the processor is either in the registers or in the stack, or memory, however you're saving information. Sometimes you need to access and manipulate the state of the processor or overwrite some of the state of the processor. So what you have to do is when you're going to handle an interrupt, you have to make sure that handling the interrupt doesn't mess up your program. So you've got to stop what you're doing, save what you're doing, go over here, handle the interrupt, do whatever whacking of whatever you're going to do, and then go back, unfreeze your program by restoring the state that you were in. So you got to push pause and unpause, and this pause has to save the state of the processor. You have to save whatever you were doing at the time so that you can restore it when you go and you finish handling the interrupt. So you've got this procedure that looks like this. You freeze, save the state, you run your interrupt handler, you restore the state, and then you unfreeze. What state do we save? What is state? What do we mean by that? So when you think about state, you think about what you remember. What does the process record? What's the information that it keeps a hold of? So if I calculate some number and I'm going to do another calculation based on that number, I have to remember what this number is in order to do the next calculation. Any state information is the information that you record or that you hold or that you remember in some way. How do I remember or record information? I write it to a location that holds data. What holds data in a processor? Registers? Memory locations? I can hold it on the stack. I can hold it in global memory. I can hold it on the heap. But variables are all held somewhere in a processor in a location in hardware that has the capability of recording and remembering information. Okay. Processors operate on registers. What you do is you take variables that are located in these locations that hold information, you load that into registers, you operate them, and then you update the state of the processor. That's just the typical operation of a program. You have data in memory, you grab the data that's in memory into registers, you operate on it, and you push it back out to memory, and that process, that cycle continues. An unfortunate consequence of using registers is the fact that you have replicated state. You have state in memory and state inside the processor, inside the registers. So we have to worry about how to manage the registers of the processor when we're saving the state of the processor. So in order to do that, we have to know about the registers of the ARM. So the ARM core has several general purpose registers. So in particular, we have 16 general purpose registers and the CPSR. The CPSR is the current program status register. What it does is it contains bit fields that tells you what's going on right now. It says what is the current processor mode. It tells you what the condition codes are. Under x86, we have condition codes. ARM has similar condition codes. So these are set whenever you're doing math operations, and it says whether the last operation indicated a greater than, or was negative, or was a result, or we had a sign bit, or so those condition codes are all kept in the CPSR register. Okay. We also have a bit there that configures whether or not interrupts are enabled. We have several other status bits. Those are all held in the CPSR. R0 through R15, these are the general purpose registers. Some of them have special uses, so general purpose can be a misnomer at times. R15 is the program counter. So this contains this register contains the address of the next instruction we're executing. So under x86, that's the EIP. Under ARM, we just refer to it as R15, or it also has an alias PC. Rule of thumb, don't write to the program counter. Use instructions to write to the program counter. Don't you write to the program counter. So the way you write to the program counter is you use an instruction that's equivalent to a jump. But don't move a value into the program counter. That'll mess things up. You can read from the program counter. That's not a problem, but don't write to it. Okay. R14 is called the link register. We don't have a link register in x86. What we use R14 for is to hold the return address from a procedure call. So under the typical C calling convention, you push your arguments onto the stack, you push the return address, you jump to the function you're jumping to. When the function is done, it pops the return address, it jumps to the return address, and then the caller pops the arguments off of the stack. This involves a lot of pushing and popping. We don't like to push and pop because memory accesses can be expensive and can be ridiculously expensive if they cause a page fault. So what the designers of the ARM core did is they said, well, okay, we are going to use a register to pass parameters, and we're going to use a register to hold the return address. We'll call it the link register. It's R14. So every time you do the equivalent of a call instruction, it takes the contents of the program counter and copies it into R14. So that just saves the return address. And if you remember, at the point where you're executing a particular instruction, your program counter contains the address not of that current instruction, but of the next one. Okay? So the program counter, whenever you're executing the equivalent of a call instruction, the PC register already has the location of the return address in it. So when you effectively execute the equivalent of the call, it'll just copy PC into R14. And then it'll do an absolute jump to the address where you're jumping to. Okay? So R14 is the link register. So if you have, in looking at the ARM assembly files that I've told you need to look at for Lab 2, and you've seen BL, specifically BL main or BL memset, BL means branch and link. That's the x86 equivalent, or that's the ARM equivalent of the x86's call instruction. So that means jump to the following label, but link first. And what link means is copy the PC into R14. Okay. Then we have R13. R13 is the stack pointer. The stack pointer holds the address of the most recently pushed item. This is the same thing as in x86. So your stack pointer points to the last thing you pushed. You can configure a stack inside ARM to point at the next location where you're going to push, as opposed to pointing at the last location you pushed. But it's significant and very important that we remember that how we actually use this is the stack pointer points to a full stack. It points to the last thing you pushed. Okay? Stacks grow from high addresses to low addresses. So the stack pointer register is used to access the stack. We can on a push operation, we decrement the stack pointer and we copy the value that we're pushing onto wherever the newly decremented stack pointer points. On a pop, we copy whatever the stack pointer points to into a register, and then we increment the stack pointer. Okay. You can use other registers to take on special roles as well, but these are the three that are most important for our discussion. You've got R15, which is the program counter, R14 is the link register, R13 is the stack pointer. Okay. With an interrupt, you need to save state. State is kept in memory, state is kept on the stack, state is kept in the heap, state is kept in registers. Okay? How do you keep from messing up the registers? When you execute an interrupt handler, that interrupt handler may need, and probably will need, to access registers. It needs to load some values into registers, take those contents of the registers, maybe do some math on them and output stuff. How do you keep from messing the contents of those registers up when you run the interrupt controller? There's no way really for the host or for the code that's getting interrupted to know that it's getting interrupted. It is just running its own thing, and then the hardware causes the program counter to stop incrementing at a particular point as soon as the interrupt arrives, and you go and you start executing other code. There isn't a way for this guy to say, oh, yeah, I'm getting interrupted now. I'm going to save my state and then let the interrupt handler go and handle the interrupt. So we have to have some mechanism for first saving state. How do we do that? Well, the first thing that we do inside the interrupt before we whack any registers is we save them all. Okay. That's all well and good, but state is maintained in other locations besides the registers. State is maintained on the stack. Why is state maintained on the stack? Where do you allocate your local variables? I don't know of any place that's a yeah. Okay, so local variables are allocated on the stack. I hope you can appreciate the fact that those local variables represent state of your program, because you can call a function which calls another function which calls another function and 20 calls deep in a call chain, each of those could have, 10, 15 local variables, and all of those local variables, the values that are stored in them, the behavior of the program depends on those variables not getting whacked asynchronously by an interrupt handler. So we somehow have to protect those values there. Well, what happens if you're currently running and you run an interrupt controller and your interrupt handler decides to go and mess around with a stack? Maybe it pops 10 values off of the stack. Well, all of a sudden you've just messed up the program that runs. So what we want to do is we want to keep the interrupt handler from messing up the stack. How do we do that? Well, just make sure your interrupt handler behaves properly. If it needs stack space, just take wherever the current stack pointer points and push stuff on and then pop stuff off when you're done. So if you need stack space, make sure you allocate it in the same way that is done regularly and deallocate it when you're done. The whole trick is just make sure the stack pointer points to where it was pointing to when you started. Okay, better yet, how about we don't let the interrupt code access the stack that your program is using? Let's give the interrupt code its own stack. Nothing magical about stack. Stack is just RAM. It's just RAM that's in a reserved area that you happen to be using as a stack. So if we let the interrupt handler have its own stack pointer that points over to a different stack, well, then what we're doing is we're guaranteeing that these two guys are separate. That provides an even better benefit from a security perspective. And those of you who had 3720 looked at the buffer lab, and if you've ever studied buffer overflow attacks occur because a user allows a client, whether that client be so a program allows some type of client, whether that client be somebody who's running on the command line or a program you're downloading from the internet, somehow you allow the access to an external entity to your stack, and you end up overriding your return address on the stack. By overriding the return address on your stack, you allow the entity that's not your program decide where you're going to return to when you return from a function call. And so that allows them to control where your program is going. So buffer overflows are a problem because it can cause major security hazards. If you have that occur inside an interrupt, this becomes a big problem because under normal circumstances, if your program gets hacked, you're running in user mode, which is an unprivileged mode of the processor. If you have a buffer overflow attack impact an interrupt, the interrupt is running in a privileged mode of the processor. As soon as you get a buffer overflow attack hitting you while you're in a privileged mode in the processor, all of a sudden you can give a third party control of your computer in a privileged mode. They can overwrite your operating system when you do that. Okay? That just takes down your machine completely. That's totally just pulling the pants down on everything. That's bad. So the designers of ARM decided as a means of enhancing and protecting the security of the programs that are running on the processor, we will have the interrupt handlers all get their own stack. Okay. So the benefits of that: minimize the interaction between the interrupt handlers and the user code, and it significantly improves security. Okay, so a word on nomenclature. So we have, there we go. An interrupt is called an exception in the hardware world. So when you're reading hardware documentation and you're looking at exceptions, don't think C++ exception. Think interrupt. Okay, they mean the same thing. They rarely say interrupt. Sometimes they do, but usually they call it an exception. An exception is an exception to the normal way in which code runs. So the ARM architecture supports several different classes of exceptions. We're going to define different classes of exceptions, and on each class of exception, there is a corresponding processor mode. Okay, when you're normally running code, supposing the ARM actually had an operating system on it that was in charge of everything, and then we were just writing a program that ran under that operating system, the processor would currently, when our program runs, be in a user mode. That's an unprivileged mode. So we have several different classes of exceptions and their corresponding processor mode that the processor uses when it needs to run privileged instructions or it needs to run in a privileged mode. So when you get an interrupt, we have the IRQ exception class. It has the corresponding IRQ mode. And then we have the FIQ exception class, has the FIQ exception mode. SWI exception class, this is called software interrupt, we run in supervisor mode. And we have an undefined instruction exception that runs in undefined mode. Now note, this is not, the mode isn't defined. It's the mode that runs is named undefined. Okay? So it's not that we're not defining what happens. So whenever you get an undefined instruction, you run in the undefined mode. There's a few others. The reset class runs in supervisor mode. The prefetch abort runs in abort mode. Data abort runs in abort mode. The ones that are highlighted up there are the ones that we pay attention to, the IRQ mode and the supervisor mode. Because we don't have an operating system, the code that you write acts as the operating system. Because of that, we are running our code in a privileged mode of the processor. What privileged mode are we using? Supervisor mode. Okay? Whenever we run an exception or an interrupt, the mode of the processor automatically switches to IRQ mode. Okay? So the difference between these two modes, you usually don't have to worry too much about. But it will be painfully significant as we talk about how you actually do a context switch. And it will impact, to a very large degree, the complexity of a block of code that we will talk about here in a couple weeks. So do be aware, the processor has multiple modes, and it will, in hardware, switch between those modes when you have appropriate transitions, like going from running your program to running an interrupt. Okay. We talked about privilege mode, user mode. Okay. And then user mode, running programs in user mode, which we aren't doing in this class, but when you are running in a non-embedded environment, or when you're running in an embedded environment that has exposure to run programs that you don't know about before you compile your programs, you typically want to run those programs in user mode, in unprivileged mode. And that separates your code from the operating system and allows the operating system to keep rogue programs from blasting all the other programs that are running. For example, that feature of having user programs run in user mode, when you dereference a null pointer and Windows pops up the box that says, you're dereferencing a null pointer, I'm going to shut you down, and you get shut down, I hope you understand that that's actually a feature. That's helpful. You don't have that helpful utility when you're talking about when you dereference a null pointer on our board. Okay? So the problem there is that we don't have such features to detect and to monitor memory protection issues. So the operating system can be this helping hand that will detect when your program is doing something it's not supposed to do and will kill your program when it detects those situations. So having different privilege modes on your processor allows you to separate the execution of privileged code from unprivileged code and keeps you from shooting yourself in the foot. So when you're in a privileged mode, you are allowed to access all privileged instructions. When you are in an unprivileged mode, there are certain instructions you are not allowed to run. If you attempt to run them, then the processor will throw an exception and say this process is doing something it shouldn't do. Okay? What are the instructions that are privileged? Well, obviously, if you're in an unprivileged mode, you can't change the mode. Because otherwise you say, well, I'm just going to make myself into IRQ mode or a supervisor mode. So the whole idea is you can't let the unprivileged class become the privileged class. Yes, we are discriminatory inside processors. Okay. You can't execute instructions to access or modify the memory management tasks. Okay, this is the critical aspect of what separates operating system code from regular user code. So the memory management unit is a hardware unit that's built into the processor that allows you to specify which regions in memory is a particular process permitted to access and which regions in memory are no processes permitted to access. The reason why that's important is because if you have a rogue process that attempts to attack the operating system, it might want to overwrite some of the operating system code. If you just mark the regions where the operating system resides as privileged only, then user code can't access them. The hardware will prevent attacks on the operating system code. Likewise, we can mark address 0 as a protected address. And so what that causes is an exception to happen whenever you attempt to access address 0, and then the operating system can tell you you're dereferencing a null pointer. So, feature, not a bug. There are a few other instructions that are privileged instructions, but basically mode changing and accessing memory management unit are the two of them that are most important. If I'm in user mode, what do I need to do if I want to execute a privileged instruction? Well, you can't execute a privileged instruction. What you can do is you can request privileged code to access and to execute the privileged instruction. How does that happen? So if the operating system is in charge of doing privileged operations, if let's say, for example, you wanted to print to the screen, well, the facilities for printing to the screen are contained in a device driver. The device driver code runs as part of the operating system, and therefore that runs in a protected privileged mode. Okay? So how do you, Mr. User Program, access the facilities to print to the screen? Well, you carry all of your code through printf, and that does all of the format conversions and builds a string of characters that you want to display to the screen. Then what you want to do is hand that string off to the operating system. How do I do that? Well, I cause an exception to be thrown. So exceptions are the key to how you transform the mode of the processor from unprivileged to privileged. So you set up your string of characters, and then you execute what's called a trap instruction or a software interrupt. And so what that does is it causes the operating system to take over. It says, yes, somebody wants a service. You pass an index indicating what is the service. That service is indicating a system call or a number of a system call. So the operating system manages all of this material after you've been through all this stuff in printf. When you get down to the function that inside the code that you're looking at for Lab 2, when you get down to the code that accesses a serial port, in a real operating system environment, that code would not be there to access the serial port. What you would have is a trap instruction that would be in there that would then allow the operating system to access the serial port. That way it would separate the code that your user is running from the code that the operating system runs, which actually accesses hardware. But the trap instruction causes an interrupt, and that interrupt causes the processor mode to change state, and then the operating system takes over. It keeps the user code from being able to access those things that are protected. It keeps the operating system separated and protected from the user code. Okay. Now, we have to deal with this concept of banked or shadow registers. Because of the fact that when we switch modes, what we want to do is we want to allow in the new mode, say we're running an interrupt, an IRQ interrupt, we want that IRQ interrupt to have its own stack. How the ARM architecture has been developed to facilitate that is they just assign, they have multiple stack pointer registers. You can only access one, the one corresponding to your mode. So when you switch mode, the hardware implicitly toggles which stack pointer register you get to access. So what we have is a diagram that looks kind of like, not kind of like, it looks exactly like this. There we go. Okay. Okay, so this is in the ARM reference manual. What we have over here are the various modes. So user, system, supervisor, abort, undefined, interrupt, and fast interrupt. These are the various modes supported by the ARM. The modes, everything but user, are privileged modes. Okay? Then we also have, of the privileged modes, some of those modes are exception modes. Supervisor through fast interrupt are all exception modes. System mode is a privileged mode, but not an exception mode. So under normal circumstances, your operating system would run under system mode. Okay. We normally, just because we chose to do so, execute in supervisor mode. So in this class, we never touch user mode, but just be aware that it's there. Our interrupts run in interrupt mode. Okay? So when you scan down in here, you can see that we've got various registers. R0, everybody has access to an R0, all the way. If you look down here at R13 and R14 and scan across here, what you can see is these little triangles that are beside here. What this means right here, so R13 that you would access in user mode, if you're in supervisor mode, this says R13_SVC. What that indicates is that the R13 register, which is a stack pointer, is a different register from the user mode R13. you still access it in assembly in the same way that you access that. The code looks identical. So you'd say move from SP into here, but the actual register that the R13 or the SP accesses is different if you're in this mode from if you're in that mode. And because everybody across this horizontal bar has a little triangle, you have one stack pointer register for fast interrupt, one stack pointer register for IRQ, one for undefined, one for abort, one for SVC. But if you'll notice here, user and system both share the same stack pointer. Okay? These are called banked or shadow registers. Okay? In fast interrupt mode, you have a whole series of banked or shadow registers from R8 all the way up. And what those guys do is they allow you to write very fast interrupt code. So if you have a fast interrupt and you can write an interrupt handler that makes use of just these registers R8 through R12 when it's processing its interrupt handler, you don't need to ever push a register or pop a register in order to save state. So FIQ is designed for very small, very fast interrupt handlers. We are not going to be writing very small, very fast interrupt handlers. We're going to be writing interrupt handlers in C that sometimes take a lot of processing. So we use IRQ mode. So IRQ has its own link register and its own stack pointer register. Yeah.
So when you're in, for example, supervisor mode, you're using a different stack pointer for those two, right? In the user mode.
Right? So yes, when you're in supervisor mode, you're using a different stack pointer than in supervisor mode and user mode. They two,
so
yes.
Let's say you're in user mode, you obviously don't have access to those stack pointers, right?
So in user mode, you don't have access. Yeah.
Wait until you're in supervisor mode?
Yeah. So there are 1, 2, 3, 4, 5, 6 physical registers in the machine that are stack pointer registers. 5 of the 6 cannot be accessed at any one time. So you only access one of them at a time. And in order to access a different one, you have to change mode. And we will look at we will have to change mode from interrupt mode to supervisor mode and back and forth to be able to toggle between which stack pointer we're accessing when we look at some code later on. Okay. We good with banked registers? Fire hosing you with a lot of architecture information today. So anyway, okay. FIQ has many other banked registers. We use IRQ mode. Most of our interrupt handlers are written in C. IRQ gives us its own stack. So, okay, how do we save state? Okay, we have this file that is isrs.s. So as soon as we execute an interrupt, as soon as we detect that we have an interrupt, this code gets run. It runs IRQ interrupt ISR. That is the name of the function. What we have here is a .align directive that's an assembler directive that says align the following on a 4-byte boundary. Then .global IRQ interrupt ISR. This says I want the following symbol to be a global symbol. So it's instead of in C where if you define a symbol at global scope, it's global by default. In assembly, symbols are local by default. So you have to say export this symbol, please. So that's what the global IRQ interrupt ISR. This doesn't expand. These two don't expand to any instructions. They're just information for the assembler, and it reacts to them appropriately. Okay. What these STR instructions do, STR means store. So it says store the contents of R0 at the memory location indicating by SP-4. This bang here on the end, that means update the stack pointer register to the address you just calculated when you're done. So it's going to take SP-4, write R0 there, and then say SP equals SP-4. Okay? So this just pushes R0 through R12, R0 through R12, and then R14 onto the stack. We don't push R13 because SP is R13, and we're updating it as we go. And note that when we're executing these guys, we are in IRQ mode, so SP is the IRQ SP. This BL says branch and link IRQ interrupt handler. This jumps to a C function that handles our interrupts. LDR means load. So load to a register. So load from this location, from wherever SP points, into R14. Add 4 to it when you're done. Okay, so the last thing that we do is we execute a sub S into PC, R14, 4. So this says take the contents of ARG14 minus 4 from it and put that into PC. This is one of the few locations where we ever write to the program counter register. Okay? This is necessary for us to properly return from an interrupt. I don't know why they do that, but the documentation says this is how it happens. Basically, it adjusts the program counter register to point to the wrong location when we're finishing up so that we can jump back to the right spot. Mitch.
Why don't you use that same bang syntax on the popping?
Okay? So what this is doing is so this takes the contents of SP. So the question is, why don't we use the same syntax for loading as we did for storing? So this takes SP and minuses 4 from it and accesses the effective address of SP minus 4 and then updates the result. So what this does is it says take the contents of SP as it is and reference memory from there. And then when you're done referencing memory, take 4, add it to SP, and make SP be the result. So one's a post increment and the other's a pre increment. So I explain that here on the next page of notes. SP comma pound minus 4 bracket bang. What that says, the brackets mean access a memory location. The pound minus 4 means the immediate number, negative 4, base 10. In brackets, SP comma minus 4, that says access the memory location pointed to by the contents of the stack pointer register decremented by 4. The bang says write to SP after you're done the contents of SP minus 4. This syntax over here that we're using on the load side, where we're saying SP comma 4, this says access the contents of memory at SP and then add 4 to it. So we don't need a bang on here because the fact that this comma pound 4 happens after the brackets, that says the same thing as the bang would. So you can use the pre-decrement that we used before to access a memory location without updating the stack pointer register. So you put the bang on there. If you want the stack pointer register updated, you leave it off if you don't. Over here, there's no way to, this syntax implies you have to update SP, because otherwise you wouldn't have the pound negative 4, the pound 4 there. So, all right. IRQ interrupt handler. This is a C function which handles all the IRQ interrupts. Now wait a minute. What happens if we have multiple types of interrupts? What if we have multiple interrupts that we're going to have in our system? Why do we have one C function to handle them all? Your ARM core only has one IRQ line. It only supports one class of IRQ interrupt. So you can only have one IRQ interrupt at all. So how do we have multiple interrupts that we're going to use? Well, we have the EP9302, which comes to our rescue here. So what it does is it offers 2 vectored interrupt controller units. These vectored interrupt controller units are parts of the core, or parts of the chip, not the core. What they do is they allow users to register different types of interrupts with them and an interrupt handler address with them, and then they will manage triggering the interrupt on the core at the appropriate time when the interrupt occurs. So we use the vectored interrupt controller to manage which source of our interrupt we want to trigger the interrupt, what is the address of the routine we want to fire as soon as the interrupt source triggers. And then the vectored interrupt controller will handle triggering the actual interrupt and running the pushing and popping code that we saw before. So the next step here is to see how do you configure these VICs, how do you configure the interrupt handling, how do you configure the interrupt source, and then how do we put all that together in a program which will allow us to run a timer interrupt and an RPM interrupt. So we'll start digging into code next time. We'll just have to repeat it all anyway on the next time anyway. So I am going to post Lab 3. Lab 3 wants you to take this big bunch of kludge of C code, convert it from KNRC into ANSI C, and start fiddling around with it. I will post these notes as well. There's a discussion at the end of the notes that kind of says why you're doing it, and I'll finish that stuff off next time. But I'll let you get working on Lab 3 over the weekend. Okay? Thanks. Lab 2's due today, right? At midnight. Dum da dum.
All right.
discussing the bylaws with Mitch.